Hey there. Classic banked turn AP Physics problem. All right, this car is coming at you right now, driving in a circular path. If you were to look at it from the top, here would be your track. Car is in there and it's going in that direction. In order to turn, it's changing its direction. That means it's an acceleration. So you've got some net centripetal force at the center of the circle. Now, because of that, that means we know the center of the circle is in this direction. There has to be this net centripetal force. Everything we do today has to end up with some net centripetal force toward the center of the circle, perfectly horizontal. So we're going to keep everything on a nice XY coordinate plane as we move forward. All right, well, let's get to it then. So the first thing you want to do is figure out what forces are acting on it. So it's the one thing that we know is always acting on it. Well, whatever's touching it is acting on it. What's touching it? Earth's gravitational field and the ramp or the bank. So we'll do it one at a time. Okay, first gravity. All right, here's the center of gravity. I'm going to do it over here. Look at that. Car straight down. That's empty. All right. As a result of pulling it down, it's hitting the bank. So that means the bank is doing two things to it. It's counteracting this gravitational force. We know that there's going to be some component that counteracts that. However, the normal force, well, the word normal means perpendicular. It has to be perpendicular to the surface in that direction. So that means the actual normal force is this. And this is just a component of it. So if down here we've got theta, what is up with that thing? Then that means that this is theta as well. And then you've got the other horizontal component of it there. And we're keeping everything on that XY coordinate plane that we talked about. So if this is the normal force, this is F normal times cosine theta. This is F normal sine theta. How do you feel about that? So of this, we can equate these two guys because they're in the same direction. Then we also know that this is going to be key to our centripetal force. It's definitely going to figure in there because it's on that XY coordinate plane that we talked about. All right, so there's our forces so far. But what about friction? That's always going to come up in these things. So talk about how to handle that. All right, friction is provided by the surface here, and it always opposes motion. So imagine if this were ice. If there were no friction, what would the car do? The car would slide off the top of the ramp. So friction is going to oppose that. Friction, let's do, I guess. So friction is going to be in a net direction this way. But that doesn't adhere to our XY coordinate plane that we're trying to do. So instead, we'll say that there's a frictional component here and frictional component down, where theta is again right there. So we know that you've got the net frictional force in that direction, which is going to be mu times the normal force. And then you've got this horizontal component, which is going to be mu times the normal force times cosine theta. And then the vertical part, which is going to be mu Fn sine theta. So what's it all mean? Well, the forces that matter for centripetal force are right there. Those two guys are going to add up to be the centripetal force pushing in. So then you can have a situation where you say Fc equals Fn sine theta plus mu and cosine theta. We also know that Fc equals mv squared over r. So what you can do is set this equation equal to this equation and then solve. Good times. All right, good luck. Oh, and I should mention that this also matters for the verticals. So you get your 3 vertical forces and you've got your 2 horizontal forces. All right, carry on to it.